Hello everyone, I hope all are you doing great. Here I'm with a new video on a Schiff-based reaction. I'm gonna go through a little background, reaction mechanism, reaction setup, and some interesting application of this Schiff-base in different fields of chemistry like material chemistry, drug delivery, catalyst activity. So let's start then. Please watch the full video. You will definitely get something from this video. Let's start. So He base is a compound with the general structure R1, R2, C double bond and R prime, where R prime cannot be hydrogen. So if you see here, this is a group specific reaction for aldehydes. So if you use any aldehyde with the primary amine, so it will form this Schiff base, nitrogen carbon double bond plus one molecule of water. So this R1 cannot be hydrogen. So this Schiff base derived from an aniline, where R1 is a phenyl or a substituted phenyl, can be called an anyl. The reaction usually occurs under basic conditions with aromatic amines to form a Schiff base, but it is also can occur under acid catalytic condition. Aniline is normally used to form a colored anyl or Schiff's base with an aldehyde. So Hugo Schiff, who born in 1835, 34, 26 April, was an Italian naturalized chemist. Originally, he is from Germany, the son of a Jewish businessman and brother of the psychologist Moritz Schiff, was German by nationality. So he discovered Schiff bases and other imines and was responsible for research into aldehydes, leading to his development of the Schiff test. He also worked in the field of amino acids and the biurate reagent. So what is the mechanism of this reaction? So first, amine act as a nucleophile, so it will do a nucleophilic attack in this carbonyl group, and then it will form this intermediate adduct, and here this negative oxygen will take this hydrogen and the electron will given to this nitrogen to form neutral nitrogen, and here this OH will take this hydrogen to removed as water. So this is a single bond, so it will give a rotation and it will go to the same side, so syn elimination actually. So it will form a syn elimination to form a double bond. So here is the Schiff base and water molecule. So see, if you see, the reaction is like equilibrium reaction. So in the reaction, if you produce water and if somehow you can remove that water, then the reaction will be going to the forward direction. That means more of the Schiff base will be produced. So that's why in this reaction normally people use molecular sieves or maybe some drying agent. So molecular sieves is the most common. So carbohydrates can be visualized with the 4-amino benzoic acid with the formation of colored and fluorescent Schiff bases, the very common use. A similar reaction mechanism occurs with 2-amino biphenyl for aldehyde detection. One of the most sensitive reagents for reducing sugar visualization, the aniline phthalate reagent, is also a Schiff base reaction. The term Schiff base is normally applied to these compounds when they are being used as ligands to form coordinated complexes with metal ions. Such complexes occur naturally. For instance, in chlorine, that is naturally occurring, like vitamin B12, you can see the chlorine unit. But the majority of Schiff bases are artificial and are used to form mainly important catalysts such as Jacobson's catalyst. So this middle molecule, this is called silane. So you can clearly see it can be formed like 2-hydroxybenzaldehyde, 2 molecule, and diamine. So it is forming the Schiff base here, di Schiff base, and these molecules are normally called silane, and they are used as a tetradentate ligand that becomes deprotonated upon complexation. So by using this, you can see one copper complex is this silane, and another is like Jacobson's catalyst made from this silane. Like this is also Schiff base. Normally Schiff bases are colored compound. The Schiff bases can be synthesized from aliphatic or aromatic amine and a carbonyl compound by nucleophilic addition, forming a hemiaminal, followed by a dehydration to generate an imine. In a typical reaction, for here the example 4,4' oxydianiline reacts with orthobenylene to give this kind of reactions. This is Schiff base. So this is an example by using the Schiff base reaction to form the foldamer. One of my colleague Birasi Kirinda, he made these foldamers by using the Schiff base reaction. So here he used basically this orthophenylene polylinker using the R as a amine group at the end, and as a linker he used dialdehyde, like with the increasing linker dialdehyde, to make the smaller foldamer or like macrocycle or the bigger macrocycle. So this paper is published in Chemical Science in 2021. Here is the information about this paper. You can go through to see how he did. I'm going to show the same technique how to set up the reaction here just right after this part. Then you can see like how he did this reaction. So the foldamer and the linker, it form this Schiff base reaction to give the macrocycles. And here he published another paper on similar work. So again the linker like dialdehyde by using benzene or biphenyl or like alkyne type compounds to make this, and it also shows like assembly of this macrocycle, how they are happening, like ring size and stability. If you are interested, you can read this paper. This is also published in ChemSci in 2019. So let's see how to set up these kind of reactions to use Schiff base to make the Schiff base, and what are the precautions you have to take care. I'm now showing the video how I set up this kind of reactions. Let's say that. Hi everyone. So here I'm going to show you how to set up reaction for Schiff base reaction, and how to work up the reaction, and what are the precautions you need to take care of during workup, NMR check, and purification. So let's see how I'm going to set up the reaction here. So here I have taken a 3-necked round bottom flask equipped with magnetic stir bar and 3 rubber septa. You can also use 2-necked flask, it's fine. And this flask is under nitrogen inert atmosphere, so I have connected a tube here and 1 rubber septa openable, so that you can adjust or adding the solid and other things. So here like you can open while the gas is on, so it will be still under nitrogen. So you can also degas it if you have the double manifold system. So here I have measured amine. I'm not disclosing what kind of amine and what kind of aldehyde I'm using, so I'm adding the amine here in the reaction flask under nitrogen. Now I closed the flask, and I'm measuring some other things. Here the molecular sieves, you can use 4 angstrom size molecular sieves, which should be really dry, vacuum oven dried. So I'm adding the molecular sieves because as my previous discussion, molecular sieves should be used to remove the produced water in the reaction to move forward the reaction to forward direction, because it is in equilibrium. It forms the water and the Schiff base form. So in presence of water, Schiff base can break down to amine and aldehyde back. So here I'm using anhydrous dichloromethane. So there are lots of solvent you can use for this kind of reactions, like methanol, ethanol, or like dichloromethane, chloroform, based on your reaction system and solubility of your starting material. So I'm going to use the trichloromethane, anhydrous dichloromethane here. So what I was saying, so molecular sieves will take out your water from the reaction, and it will make your ship base stable in the reaction. That's why you have to use molecular sieves. But if you search for literature, you might see other options also, some other drying agent for these kind of reactions. So here I'm using the DCM to dissolve my amine, and once the solvent addition is done, then I'm going to use my aldehyde through rubber septa. Normally aldehydes become like aldehydes are like liquid, but sometimes your aldehyde may be solid, so you can measure out your aldehyde in a vial and dissolve it in your same solvent like dichloromethane. If you use dichloromethane or the solvent you are using, then take in like this syringe, and you can add slowly dropwise in the reaction system. So here I'm adding the aldehyde, and once my aldehyde addition is done, then I'm gonna use a catalytic amount of trifluoroacetic acid to do the reaction faster, like acid catalyzed reaction. So once I added the aldehyde, so I will start stirring the magnetic bar. In between this time, I will also make ready the trifluoroacetic acid to add in the reaction system. So here is the trifluoroacetic acid bottle. So I will take like 0.1 milliliter based on your reaction scale. So actually it is like 0.08 milliliter. So you can do your calculation, and you can go to the literature how much equivalent or millimole they use. So I'm using like my required amount, so it should be added dropwise very slowly. And once it is done, the addition is done, then you can stir your reaction for desired time according to your procedure or like literature procedure you are following. So based on different reaction might have different reaction time. So for me it is 24 hours, so I'll start this reaction for 24 hours at room temperature. If you search literature, you might see some reaction also may require the temperature. I'm not sure yet, but this reaction normally is being done at room temperature. So I'm stirring the reaction system at room temperature for as I mentioned, like you can stir it for desired time at room temperature, but I'm gonna stir it for 24 hours. Okay, after 24 hour of the reaction time, I'm quenching the reaction with dry triethylamine or anhydrous triethylamine. Again, these reactions need to be water free. So any reagent, any solvent you are handling or working, you must think about presence of water or not. So make sure that whatever you are using, those should be anhydrous, no water. So you can make anhydrous solvent, anhydrous reagent. So before setting the reaction, you should think about it. So here I'm adding like triethylamine to quench the reaction. Actually, I'm just neutralizing the TFA since I added the TFA. So, and also the Schiff base is amine actually, so it should be stable in base form. So triethylamine will not be a problem, but it can remove the neutralize the trifluoroacetic acid. In some cases, people also use acetic acid to catalyze the reaction. So here I'm using trifluoroacetic acid. So once the reaction is quenched, like you might see some fume is forming inside, like until it neutralization. So once it is done, like stir for 5 to 10 minutes after addition of the triethylamine, then you can open up your rubber septa and take a pipette valve and a pipette. Then you can transfer that liquid in a vial or another round bottom flask to do the rotobep. So here I am transferring the liquid in a clean vial, dry vial, so that there is no water, otherwise your compound will be breakdown. And another thing, sheep bases are normally the colored compound. mm, so here you can see like very nice colored solution. Even if you use both starting material is colorless, still you might see the colored compound, because sheep bases normally give colored compound. So here I'm transferring this solution in a vial. Once it is done, then I'll do rotobep. And after taking all liquid, you can use the same dry anhydrous solvent again to wash out the remaining part, and then you can use more rinsing. So with the pipette, just transfer that remaining rinsed solution to the same vial, and then you can do the rotobep to remove that solvent. So these kind of sheep bases are normally stable around 40, 50, 60 degree, even 70 degrees Celsius also, but it depends. Different compound could be different stability. So in that case, you can use rotobep, and water bath shouldn't be like too high temperature. You can use 30 to 40 or like 50 degrees Celsius maximum if your solvent is other than the DCM, like methanol or ethanol. So you might use little bit temperature, but initially don't try to use the temperature. Try to use room temperature. Under vacuum pressure, the boiling point of the solvent always decreased, so ethanol or methanol also can be gone with the rotobep. And then you can use vacuum pump to dry remaining solvent. So here my rotobep is done. Still it is showing liquidish. This compound could be solid or liquid or gummy liquid. So now I am using my like vacuum pump to dry the remaining trace amount of the solvent. So once it is dried, then I will start thinking of purification. So there are a couple of things you need to remember. You cannot use silica gel for this purpose, like to purify your compound. So it is done. I'm taking out my crude. So what I was saying, you should not use silica gel. And also, if you want to take the proton NMR or carbon NMR of this crude material or like purified material, definitely for the sheep base, you should neutralize your CDCl3 to do the NMR. If you don't know how to neutralize CDCl3, please watch my previous video on this. Like I uploaded one video like how to make the neutralize CDCl3. So here is the silica gel. I'm showing like do not use silica gel to purify this sheep bases. It is like, because silica gel is since I told the CDCl3 neutralized, so you can take some alumina in a pipette and then filter CDCl3, then it will be neutralized to a vial. So you can watch my previous video. As I was saying, like silica gel is a little bit acidic, so if you use this sheep base to purify silica gel, then it will be break down. So here I'm writing some summarized situation, so you can keep in your mind while you're making your sheep base. So hopefully this video will help you to set up the reaction, to understand the reaction, and experience to do these reactions and to handle these sheep bases. As I mentioned, acid sensitive, water sensitive, silica gel sensitive. But another thing you can remember, to purify this kind of compound, if the molecule is high or larger molecular weight, so you can easily purify this type of sheep base by using GPC or gel permeable chromatography technique. So you can use GPC to purify this compound. Sometimes people also can use alumina, basic alumina, to purify the compound. So let's see what is the acid catalyzed Schiff base reaction mechanism. Here, first your used aldehyde will be protonated to form this kind of intermediate, and then the amine will attack this carbon with its lone pair of electron to form this adduct. So nitrogen become positive in charge, and this hydrogen will give this electron to this nitrogen, and it will form this aminal type compound. And then in presence of this proton, like acidic proton or acid, you are using already acid, so this oxygen will be protonated again to kick out as a water from this reaction. So this bond will be break down, and this carbon will be forming a carbocation with this water molecule, and then molecular sieves actually will take out your water to make this intermediate stable, and this lone pair of the electron will go there to the carbon to make the double bond, and it will form a positive charge here. Now this hydrogen will be going as a H plus, since it is acid catalyzed, so the catalyst is coming back to give you the Schiff base. So this is very simple, almost similar as the mechanism previous I have shown. So let's see some nice interesting application of this kind of Schiff base reactions. So most of the time the people use Schiff bases as a ligand, like ligand synthesis to form metal complexes for catalyst or material science purpose. So it can be used as a catalyst. These Schiff bases can be used drug delivery and biological application, and Schiff bases are investigated for antimicrobial, antiviral, and anti-cancer activity. They have also been considered for the inhibition of amyloid beta aggregation. So Schiff bases are common enzymatic intermediate where an amine, such as the terminal group of a lysine residue, reversibly reacts with an aldehyde or ketone of a cofactor or substrate. The common enzyme cofactor pyridoxal phosphate (PLP) forms a Schiff base with a lysine residue and is transaldehyminated to the substrates. Similarly, the cofactor retinol, which is in our eyes, forms a Schiff base in rhodopsins, including human rhodopsin by a lysine 296, which is key in the photoreception mechanism. So here is one example. If you are interested to read this paper, Beauty in Chemistry Making Artistic Molecules with Schiff Bases. So I just found this paper and I was thinking like just to show some of the nice beautiful molecule by making the Schiff base. So here the Schiff base like this kind of Salen type compound, not Salen actually, this kind of ligand in the Schiff base, and if you use copper ion, so it formed this copper kind of ligand, and similarly the Salen molecule with the copper, so it formed this kind of nice molecules. There are some more examples here. So basically the reaction, if you watch it, so salicylaldehyde is used with the ethylene diamine to form this Salen type compound. Since it is forming from the salicylaldehyde, and that's why it is called Salen, it acts as a ligand. So if you use a metal, so metal, it will form a metal ligand type things. So here they use dialdehyde and triamine. So these kind of reactions is forming this compound which is called bistren. So this compound also can be used to make like metal complex or like other chlorate complex for the application of the material chemistry. So if you are interested, you can read this paper. I just wanted to show like how the Schiff base is applied in this kind of complex chemistry. And they also have shown in the same paper, like they made helical compound but with the metal ion. So same, they use ketone type compound with the amine to form this bigger molecule, which can go like uh, helical direction with the metal ion. And also, if you use same amine and aldehyde in the same group, it can go polymerization, but in presence of some metal salt or metal catalyst or something, they form like chlorine type thing, red crystalline complex salt. So here also like it is forming the Schiff base. Also here it is Schiff base, but in it mediated by this nickel catalyst. There is another nice molecule which is made by Sir Stoddard Fraser. You know that he is a renowned Nobel laureate. So in his group, they make this compound, the boro boromine rings. So the one part synthesis was carried out in refluxing methanol in the presence of zinc um, trifluoroacetate. The hexametallic complex is depicted is an orthogonal representation, so it is also a nice molecule. There is another paper, recent advances in Schiff-based ruthenium metal complex synthesis and applications. There are lots of example are given in this paper. I'm just showing a couple of reactions here, like they use a primary amine and this like aldehyde in methanol reflux. That means they did heat this reaction, and to form this preliminary Schiff base, which was being used for the ruthenium to make this kind of complex. um, More the same in the from the same paper they used like the Schiff base and then later ruthenium complex. And here are more example. So they use RNH2 and aldehyde to form the Schiff base, and with the ruthenium catalyst like triphenyl phosphine ruthenium chloride it to give this kind of new complex. And there are lots of change of the R group also there. And here also you can see like aldehyde and the amine forming the Schiff base and ruthenium complex. So actually if you interested to go more details about those, you can read that paper on the ruthenium from my link. I have shown the paper. So these are like monodentate, tridentate, tetradentate, pentadentate, hexadentate ruthenium complex. They have shown like lots of Schiff base formation, and that Schiff base also can go to like if you have the sulfur in this molecule, it can go to dithione form and dithiol form. Like just think O as a alcohol, that's why like dialcohol or diol, but since it is sulfur, so dithiol. And dithione because sulfur, oxygen, ketone, and sulfur is thione, so you can think about it. So they use this kind of Schiff base to form more complex ruthenium compound. So there are lots of example in that paper. So there is another paper, it is really interesting. These people use ferric oxide with the dopamine and functionalized manganese Schiff base complex. That is a promising magnetically separable heterogeneous catalyst for oxidative transformation. This is really interesting paper. So you can see that here they use the ferric oxide and the dopamine, and it form this kind of cluster compound. And after that they use, I guess, Jacobson catalyst, and that form another layer on that. And by doing this nanoparticle, they can easily oxidize molecules. Suppose you have diphenyl methane compound to like benzophenone, carbonyl group is attached, and alcohol to aldehyde, and also alkene to epoxide. So if you want to read this paper, you can go through this paper. It is a really interesting paper on this, like a promising magnetically separable. That means you can separate your catalyst by using magnet. Separable heterogeneous catalyst for oxidative transformation. You know, like heterogeneous means where the catalyst will be like in as a solid form, and the product will be your compounds or other reaction derivatives or product should be in the solution, so you can easily separate those compound. This is another interesting paper, like published in Camp Communication. It is also based on the sheep-based reaction. So they use dopamine and the glutaraldehyde as an aldehyde to form this spherical compound, and then they use anti-cancer drug doxorubicin, that is showing as a dox, with the linker, and a photosensitizer that is called colorin E6, or in short CE6. So these things will wrap up this sphere, and then it can be act as a drug delivery system. So this is pH responsive dopamine based nanoparticles which can be assembled by a sheep based bonds for synergistic anti-cancer therapy. So these nanoparticles exhibit pH-responsive drug release in the acidic tumor microenvironment. Also produce singlet oxygen under irradiation. So if you see, remember the molecular oxygen which is available in the atmosphere, or like we are inhaling, that molecular oxygen is triplet state. Normally gases are in like singlet state or any molecular singlet state, but oxygen is in the triplet state. So with the irradiation, this triplet oxygen can give you like singlet oxygen, which under irradiation, and that is actually can kill the cancer cell. So finally, achieving a synergistic anti-cancer effect of chemotherapy and photodynamic therapy, in short it is called PTD. It's a really good paper on this kind of sheep-based application. You can read through if you want. So the link is like Camp Communication 2020 56. So let's see more application. Another nice paper is like those people use bio-inspired and eco-friendly high-efficiency cinnamaldehyde antibacterial surfaces. How they did this? So they can kill the bacteria, live bacteria, to the dead bacteria by using cinnamaldehyde surface. But how that surface can be made? So basically they use primary amine, or like polyethylenamine and dopamine. This is the dopamine or polyethylenamine, and cinnamaldehyde, and also like some supporting substrate or something, tannic acid. So they made a surface like this antibacterial coating by using the sheep base reaction, and which can kill the bacteria. So if you're interested, you can read this paper too. Mostly the sheep base also applied in case of MOF, metal organic framework, COF, covalent organic framework, POC, poly organic cages, or not poly, sorry, porous organic cages, and dynamic covalent chemistry bond formation like DCC. Those chemistry mostly done by using sheep-based reaction with the amine and aldehyde. If you are really interested to know more about it, you can go to the uh, uh, group website of Professor Jeffrey S. Moore, who is the professor of University of Illinois Urbana-Champaign. And also there is another professor, Wei Jiang. He was the postdoc of Jeffrey Moore. Now he is a professor at University of Colorado Boulder. They do a lot of chemistry on that. And Jeffrey S. Moore also did a lot of chemistry on this aldehyde and amine kind of reactions. So one of the paper from Wei Jiang group, transformation of porous organic cages (POC) and covalent organic framework with efficient iodine vapor capture performance. Yeah, it should. I understand. Like you might be thinking what the like biggest thing. These are or like weird or maybe complex. But yeah, this is interesting. And if you have the interest on COP or like COF, MOF, COF, and POC. So you can go through those papers. So here basically they used, see that the tetraaldehyde group and the diamine, so forming this kind of sheep base. See here like double bonded, and also here also they use diamine to make the sheep base. You can see the sheep base bonding here to make those kind of compound. So I'm right now I'm not a material chemist anymore, so I'm not going through details on it. If you want to study, you can read those papers, but simply I'm showing the reaction, how they are applying these kind of reactions for like Schiff-based reactions for this kind of complex chemistry or like material chemistry to make the MOF, and porous organic uh, cages. So there is another paper, Covalent Organic Frameworks, Perspectives of Industrialization by Wei Zhao. So they also try to make this kind of compound NH2 aldehyde to make these. So you can read, if you want, you can read that paper too. So they try to show different compounds by using this chemistry and changing the linker, or like the you see like here like triphenyl, and this is like kind of biphenyling thing, so making the more bigger size of the whole. And at the end I can also say like hydrazine can also form the sheep base. So it is a very common old school chemistry test. Like for any aldehyde, if you use dinitrophenyl hydrazine for the aldehyde test, it form a very nice orange color solution, which actually confirm that yes, it is aldehyde. So DNPH was previously used always to detect the aldehyde before like early school or like college type chemistry. But there is an issue, DNPH is like kind of heat sensitive or like shock sensitive, especially if it is dry it can be explosive. So that's why it is handled as a wet powder, and it is a precursor to the drug Sibifin. So I hope my video on this total sheep based reaction will help you everyone to understand what is the chemistry, how to set up the reactions, and what are the applications in different field of studies. And if you want to dig more about it, you can just search the literature, you will get interest. So today that's it from now, and I'll bring new videos, and please subscribe my channel if you didn't do yet, and who already have done, thank you for supporting. Goodbye now.